In this screencast, we're going to talk about unimolecular elimination. So this is the E1 reaction. So elimination unimolecular, which means the rate determining step only depends on the concentration of the substrate. And again, we define the substrate as the species that's bearing the leaving group. So what are the promoting factors of E1? That differentiate it from, say, E2. So again, you're typically looking for a tertiary or secondary substrate, meaning that's the group bearing the compound bearing the leaving group, and a polar protic solvent. So again, this is, as comparison to E2, this is lack of a strong base. And we're defining a strong base in this sense as something like sodium ethoxide. So our metal cation, our negatively charged base, or something, a bulky base, potassium tert butoxide. So that's what we're defining as a strong base. Again, the polar protic solvent, these are not strong bases. So the promoting factor is something that's going to ionize the substrate to a carbocation using this solvent, and then the solvent is subsequently going to act as a weak base that deprotonates a beta hydrogen. So let's look at some examples of this. So example 1, let's consider the following substrate. So we have this starting material. We're going to treat that with sulfuric acid in the presence of water. And so we're going to end up with the following two products. This is going to be our major product. And then we're going to get a minor product. And we're going to say the following is not formed. And so we want to understand why that is as well. So let's go through and number some carbon backbones, name these things so we can communicate about what's happening through the mechanism. So our starting alcohol, we'll just number the chain 1, 2, 3, 4. That's the longest chain. So if we were to name that, we would have 3,3-dimethyl-2-butanol. So this helps us as well. When we look at this structure, we can see that it's an alcohol, and when we classify that alcohol, we're starting with a secondary alcohol. So again, these sort of activities help us determine what mechanism is at play, and through the mechanism, we can figure out things like stereochemical outcomes. So if we look at the major product that's formed, let's go ahead and put some numbers in here too. 1, 2, 3, 4. We can see that the major product is 2,3-dimethyl-2-butene. So again, the 2 in front of the parent here is telling you where the alkene starts. So we see 1, 2, that's where the alkene starts. Now let's go ahead and do that for the minor product as well. Now we're going to include the pi bond as position 1. So 1, 2, 3, 4. So we would then name this compound 2, 3 dimethyl dash 1 butene. And so if we do the same for the product that's not formed, again, even though it's not formed, we want to understand why it is not formed. 1, 2, 3, 4. So here we end up with 3 dimethyl dash 1 butene. And as a general review, you can see these are all constitutional isomers. They differ in the location of the pi bond and the substitution of the methyl groups. So when you're thinking about this, think about unique carbon, unique proton, and the sets or ratios of those protons is how you would differentiate that these things are forming. So now let's consider the mechanism of what's happening here. We're starting with sulfuric acid, which I want to represent in the following way: H plus X minus, just so I don't have to keep writing the sulfate Lewis structure over and over again. Just keep in mind that's what the X minus is. So this is sulfuric acid, this is water. So if this is an acid, this has to be the base. And of this entire structure, the electrons on the oxygen are the basic portion. So we're going to do an acid-base reaction. Our arrow is going to start at the lone pair, and we're going to protonate that oxygen. So we're setting up an equilibrium here. So our first step is protonation. I'm just going to say PT, proton transfer. And so the reason that we're doing that, again, we're balancing our charge. The reason that we're protonating the oxygen is because it has to ionize, and that's a feature in SN1 and E1 is the ionization. You cannot just have hydroxide leave because that is a base and you're in the presence of a strong acid, sulfuric acid. So you have to have it leave as water, which is already present in the medium. So next is the actual ionization event. So we're having a secondary alcohol ionize. So now this is the rate determining step. So I'm going to say RDS, rate determining step, or the slow step, is the ionization event. And again, the reason that is slow is because you are forming a high energy species, a carbocation. So we're going uphill in terms of the energy diagram. Again, we lose water is part of the ionization event. As this bond cleaves, we lose water. So we're forming this carbocation, and because we started with a secondary alcohol, so a secondary alcohol, we form a secondary carbocation. Now we are at a decision point. So carbocation stability is tertiary greater than secondary greater than primary, much, much greater than methyl. So the question we have to ask ourselves is, can this rearrange to form a more stable carbocation? Meaning, since we are at the secondary carbocation, can we rearrange to form a tertiary? Typically, you can't go and form something less stable. For example, secondary to primary, that's not energetically favorable. So how do we determine that? Let's call this the alpha carbon, and then the carbon's bonded to that beta. So we have a methyl group, and then if we look over here, we have a tertiary carbon, a quaternary carbon that has 1, 2, 3, and then of course the carbon it's bonded to, that's 4, so it's quaternary. So this is beta prime because it's different from this. And again, this is just for communicating. So it turns out that this can rearrange, and let's show that happening. So I'm gonna show an arrow going this way. So now this is a one-way arrow. Once the rearrangement occurs, it's not going backwards, so that's why this arrow type is changing. So let me write that down. Say beta prime, and then we'll say methyl. So this is a 1,2 methyl shift from the beta prime to the alpha. So when this happens, we show this moving over, meaning that this methyl group, or any one of these, they're all the same, is going to shift over. So the electrons in here migrate over. The plus charge moves from here to here. Let's draw that out. So now we end up with that. Here's our counter ion. And we classify this as now a tertiary carbocation. So now since we formed a new carbocation, we'll go ahead and now call this alpha and establish the new beta carbon. So we have beta here, and then these two methyl groups we'll call beta prime. So they're, again, equivalent. So beta prime, beta prime. So beta is not equal to the beta primes, obviously, because we have a methine. So beta equals methine, beta prime equals methyl. So the reason this is important is because we now have a choice. And the choice is basically determining what is the major and what is the minor products. So this is sort of a bifurcation. And I want to sort of draw it like that. So we see that on the energy surface, it's either going one way or another. So in the top arrow, what I'll show is so the formation of the major. The bottom, I'll show the formation of the minor. And so the top arrow results from elimination at the beta carbon. The bottom is beta prime. So what do I mean by that? I'm going to go ahead and put in that hydrogen, and I'm just going to put in one hydrogen for the beta prime, even though there's 6 of them. So that's a thing we have to contend with as well, is statistically it's a 1 versus 6 chance, but this route is taking us to the major. So we want to understand, statistically speaking, if this is less desirable, why is it major? So what happens is we can have, say, water act as a base to abstract that hydrogen. We then do an elimination to form the alkene. That gets us a tetra-substituted alkene. Alternatively, if we're going through the beta prime, and we do the elimination that way, we're now forming this compound, which is di-substituted. So the issue that we have to understand and explain is, like I said, there's only one hydrogen at this beta carbon, which is the methine. But its elimination route is preferred because we're forming a tetra-substituted alkene. The minor product results from deprotonation of beta prime, but there's 6 hydrogens. So it would seem like the conjugate base here, whatever base, would encounter the 6 more often than the 1. But it's not preferred because we form something that's more stable. So in the next couple slides, we'll look at alkene stability, and that's a big factor in determining what is the major versus the minor. Now, the reason that we do not form this is because we're simply doing an elimination from this secondary carbocation. So you can see that at this beta carbon, there's a hydrogen, and if the base comes along to deprotonate, we form the alkene here, which would form that. So if you think about the rate at which these things happen, the rate at which this carbocation, this secondary carbocation, rearranges is much faster than the elimination event from this position. So once this forms, again, it's the rate determining step here. Once that forms, it's super fast to rearrange. And then you have these different elimination manifolds. So this does not exist long enough that an elimination can happen. So that's how we rationalize that. So here's another example of an E1 reaction with a carbocation rearrangement via ring expansion. So overall, we would classify this process that's happening as we're taking an alcohol, we're doing a dehydration because we're losing the elements of H2O and we're forming an alkene. So alcohol to alkene via dehydration. So we're starting with this alcohol here. We can see it's a secondary alcohol. We're treating with phosphoric acid and heat. So it's doing an elimination to form an alkene. We get a major and a minor product. Let's go ahead and name the products. So here we have 1,2-dimethyl -1 cyclohexene. Here we have 1, 2, 3, 4, 5, 6. So this would be 2,3-dimethyl -1 cyclohexene. So notice the numbering is slightly different just to give the substituents their appropriate locant numbers. So what is the difference between the major and the minor? Again, if we look at the alkene and we classify that alkene, we have 1, 2, 3, 4 carbon substituents on the alkene. So we would say that is tetrasubstituted. Now if we do that for the minor product, we can see we have 1, 2, 3 carbon substituents, so that's trisubstituted. So the pattern here is when we're doing these eliminations, we want to form the products according to alkene stability. And we'll talk about why they follow this pattern in the next slide based on heat of hydrogenation. So that's the alkene stability 10 is tetra is greater than tri is greater than di is greater than mono. So this really dictates when we get to the carbocation which beta carbon does the elimination. So let's look at this problem. As you can see, we're basically presented with a starting material, the two different products, and we want to draw the mechanism to understand how it happens. So we've already said we're starting with a secondary alcohol. We're ending up with 2 alkenes, tetrasubstituted and trisubstituted. What you'll notice is here we're starting with a 5-membered ring. In the product we're ending up with 6-membered rings. So something that's happening is the 5-membered ring is going to a 6-membered ring. So that ties in with what we saw with carbocation rearrangements. And the reason this happens is because a 5-membered ring is slightly more strained than a 6-membered ring. So as part of the carbocation rearrangement, the ring expands to relieve ring strain. So let's go ahead and get started. I'm going to call this H plus, X minus again, where X is the phosphate anion, just so I don't have to keep redrawing the Lewis structure. So again, there really should be nothing mysterious about proposing mechanisms because what you're capturing in this information helps guide you. You know that this OH has to leave because it's not retained in the product. So hydroxide is a bad leaving group, so that's why we protonate it in the presence of acid. Again, this is a reversible proton transfer. Let's balance out our charges. We're starting neutral, we're ending up neutral. Now we've created a good leaving group. Water is a neutral leaving group, so this bond ionizes. Again, that's the rate determining step. So the slow step is the ionization because we're forming a carbocation, which is higher in energy than what we're starting with in the starting material. So this is a secondary carbocation. Again, we balance our charge. We're losing water, so we just write minus H2O. So again, when you're considering the stability of the carbocation, let's use our nomenclature: alpha, beta, beta prime. Beta is a methyl group. Beta prime is a quaternary carbon. And again, I'm calling it quaternary because it's bonded to 1, 2, 3, 4 carbons. This is going to be the driving force for rearrangement and not the beta for the following reason. So notice this is a one-way arrow at this point. And so we have a choice. We can have a methyl group shift over and give us a tertiary carbocation. Let's show that, but that's not going to be the preferred path. So here we end up with a tertiary carbocation. And again, that's one possible path. The actual path that happens is the ring actually expands. Again, we said this is a 5-membered ring. One of the ring bonds is actually going to move over. So that will migrate. So I'll draw it without too much distortion, then I'll redraw it. So this bond is the one that migrates over. The plus charge ends up where that bond just left. And so now if we count 1, 2, 3, 4, 5, 6, we can see that the ring expanded, but that looks pretty sloppy compared to what we're used to seeing. So let's actually draw it as a 6-membered ring. Let's go ahead and put our numbers back in. The numbers help us with the substituents because we see that at the 1 position there's a methyl, at the 2 position there's a methyl, but it also has the plus charge. We see that is now a tertiary carbocation. And again, the chemical intuition, even though these are both forming tertiary carbocations, is that this route is preferred because we're relieving some of that ring strain that was present in the 5-membered ring. So now here we end up with our second decision point. Because we have to re-examine now what the alpha carbon is. So here's our alpha. We have now 3 different beta. So we have beta, beta prime, and beta double prime. We can see that beta is a methyl, beta prime is methylene, and beta double prime is methine. So when we're considering the different products forming, we can see that if we eliminate from beta prime, that's going to give us a tetrasubstituted alkene. So again, that's going to be elimination of this hydrogen using the water or the conjugate base of the phosphoric acid. That's the proton transfer to do the elimination. So we'll put this route going from beta double prime, this route going from beta prime. So when that happens, this one of these hydrogens is eliminated. So now we end up with a tri-substituted. And if we were to eliminate from beta, that would be one of these methyl hydrogens. And so the reason we don't see that as a product is because if you count 1, 2, this is di-substituted. The tetrasubstituted is going to win over the tri-substituted, and this probably won't be formed in any appreciable amount because it's di-substituted according to our trend here. So in the next slide, what we'll do is understand the stability trend by looking at actual calorimetry data and heat of hydrogenation. So let's take a moment to review the orbital description of a pi bond. We'll look at some general enthalpy changes for what constitutes breaking a pi bond, and then we'll actually look at the heat of hydrogenation, which is the addition of a molecule of H2 across the pi bond. So conceptually, we've talked about that quite a bit this semester when we talk about degrees of unsaturation, with the pi bond being 1 degree of unsaturation. So experimentally, that's measured through the heat of hydrogenation. But let's refresh our memory about what an actual carbon-carbon pi bond is. So if we look at just a very general carbon backbone with 2 sp2 hybridized carbons, each having a p orbital with an electron in it, the overlap of those electrons, that forms the pi bond. So again, what conceptually is that the pi cloud is located above and below this carbon framework. So again, it's not, these electrons are not localized here, or there, or any sort of combination. They're delocalized above and below as a cloud. So again, the cloud is or more broadly put, an orbital is a region of electron density. So we sort of draw it, you can think of it as a probability of finding the electron in that space. So that's the pi cloud. So again, when we talk about forming a bond, there's always the bonding orbital and then there's the antibonding orbital. So what does a pi antibonding orbital look like? And again, this is a region where there is no electron density, but it still exists because it's used when you're forming bonds to the alkene. So basically, it's sort of a region, you can think of it as outside where the electron density in the pi cloud is. So this is the pi star orbital. And again, those things exist at the same time. So just to recap here, sp2 hybridized carbons, p orbitals, overlapping. So the total bond energy for the pi bond in general, we can say it's 611 kilojoules per mole. If we know that a typical carbon-carbon sigma bond is approximately equal to 347 kilojoules per mole, then the contribution of the pi bond itself is approximately equal to 264 kilojoules per mole. So what are we understanding from this information? The sigma bond is much stronger than the pi bond itself. So overall, these two things make up that double bond, but the sigma bond contributes more to the strength. So therefore, the first thing to break is the pi bond itself. So just as a review, because we're going to be talking quite a bit about alkenes, so if we show trans 2-butene, we recall that the pKa of a carbon H bond of an sp2 hybridized carbon is approximately 40. We know that the carbons of the alkene occur in the 120 to 150 region in the C13 spectrum. This type of hydrogen occurs between 6 to 8 parts per million in the proton spectrum. The other important thing to note is that these configurations, the trans geometrical isomer will not interconvert into the cis spontaneously. So whereas we have free rotation about a normal sigma bond, you do not have free rotation about a double bond, again, because this contribution of 260 kilojoules per mole of energy to that bond prevents rotation about that bond. So you either have to chemically break that pi bond to get rotation, or you have to put light or heat into this to make it rotate. So it does not spontaneously happen. So that's why you can tell the trans from the cis using these different methods. So now let's take a look at a reaction of alkenes that relates to alkene stability. And so this is the heat of hydrogenation. So the reaction is, generally speaking, if we're using words to describe, an alkene treated with hydrogen gas, H2, some metal being reduced to an alkane. So we've conceptually talked about this throughout the semester. An alkene has 1 degree of unsaturation. We're treating it with hydrogen gas on some metal catalyst, and it's reducing it to an alkane. So the H2 adds across the pi bond to give you the fully saturated alkane. So experimentally, that is how a degree of unsaturation is actually determined. because you can measure the amount of gas you're adding. So the volume, you convert that to moles, the moles of H2 gas reacting with the moles of alkene. So that's how you get degrees of unsaturation. So this is actually an addition reaction, as we can see. If we start with ethylene, we're adding one molecule of H2 across that pi bond. So conceptually what is happening, the alkene, which is supplying the electrons, is the Lewis base. The hydrogen molecule is the Lewis acid because it is supplying those electrons. So we're adding H2 across this bond, with this being the nucleophile, that being the electrophile, and then we end up with the alkene. This generates or evolves negative 137 kilojoules per mole. As you see in the next three examples, we have propene, butene, and pentene. So if we look at the alkene itself, we're essentially just putting an extra carbon group off each of them. And then going down, we're increasing that carbon chain. So these are all mono-substituted alkenes. Again, we're adding H2 to get the alkane. So you'll notice these basically hover all around the same value. So mono-substituted alkenes are all approximately negative 126 kilojoules per mole of energy evolved. So what I'm going to do is basically take a 4-carbon chain and plot it down here. We're just going to plot these different substrates here and look at what energy is evolved. So let me just go ahead and plot butene itself. So when this gets hydrogenated, to butane, again, that evolves negative 126 kilojoules per mole of energy. So what I'm going to do now is compare that to, if we take cis-2-butene and we hydrogenate that, again, that's going to butane. This now evolves negative 120. So it evolves less heat. So what is that telling us? This difference of 6 kilojoules per mole, this molecule is more stable than this. So the more heat you evolve in this comparison, the less stable. So the next in the trend is actually di-substituted, but a constitutional isomer. So this is 2-methylpropene. So when that's hydrogenated, you end up with 2-methylpropane. This evolves negative 117 kilojoules per mole. Now the other di-substituted example we can have is the trans constitutional isomer. So this gets hydrogenated to butane. This evolves negative 116. So you can see that the trans evolves less heat than the cis. And again, the more heat that's evolved relative to something else, the less stable. So trans is more stable than cis. We rationalize this as well based on that these methyl groups are sort of banging into one another and causing strain. So now let's look at a tri-substituted butene. When this gets hydrogenated, we end up with 2-methylbutane. This evolves negative 113. So you can see that by substituting out a hydrogen for a methyl, we're gaining some stability. So the more carbon substituents you have bonded to the alkene, the more stable it is. So now let's look at the fully substituted. When we generate 2,3-dimethyl-butane from 2,3-dimethyl-2-butene, this evolves negative 111 kilojoules per mole. So what we're saying here, the tetra is the most substituted, followed by tri. Then you have trans, disubstituted. This we would call geminal disubstituted. So geminal meaning twin, they're on the same carbon. Cis disubstituted mono. So what does all this mean for us, practically speaking? That when we're going through an elimination mechanism, we want to form the more substituted alkene when we do that elimination. And this actually has a name. This is called Zaitsev's rule. So generally, the more substituted alkene is formed in an elimination reaction because it is more stable. And that helps guide us to determining what is the major and minor product in an elimination. So to recap in this lecture, we've looked at the acid-catalyzed dehydration of alcohols to alkenes using the unimolecular elimination, where we have to consider that upon ionization to form a carbocation, the carbocation can rearrange. We do that by looking at the beta carbons and determining if it can rearrange to something more stable. We've then looked at the orbital description of an alkene, the energy associated with the pi bond component of the double bond of an alkene. We've now looked at alkene stability as related to heat of hydrogenation, which is the first addition reaction of alkenes, is adding H2 across the pi bond. And that helps us understand Zaitsev's rule, which states that the more substituted the alkene, the more stabilized it is. So we're going to use this information in further screencasts and lectures to look at different electrophiles adding to the pi bond of an alkene to make different functional groups.